Light is a particle. Number 3, the photoelectric effect. Probably one of the, what I think, one of the hardest conceptual things to understand in our physics course. So hopefully I won't bamboozle you too much, and we'll just work through it systematically and get a good understanding of what it is and the significance of it. So what's the photoelectric effect? Well, some substances, typically metals, and we're pretty much going to limit ourselves to metals, when they're illuminated by light or shorter wavelengths, and by shorter wavelengths than light, visible light, we would be talking about ultraviolets. So when we shine a light on these metals, electrons are emitted from their surface, which is a bit bizarre to think about it. You shine a light onto a metal and you get electrons jumping off the surface. Now these electrons are called, these electrons jumping off the surface are called the photoelectric effect, and the electrons are sometimes called photoelectrons. Now the electrons are emitted with a range of kinetic energies, so some of them just come off the surface and some of them come off with a velocity, and there's a maximum to that velocity depending on the situation. So let's just go through that again. If we shine light onto a metal, electrons come off the surface, and that's the photoelectric effect, and those electrons can have a range of kinetic energies up to a maximum that's dependent on the situation. And so here we have some sodium metal, and we're shining light onto the polished surface in a vacuum, of course, and you get the electrons. And so the photoelectric effect was a direct contradiction to the expectations of the classic physics at the time, and its explanation marked one of the major steps towards quantum theory. And so it followed directly on to Max Planck's work on quantum and photons, and so this further our understanding and pushed us into an area of physics that hadn't been known about. So some of the remarkable aspects of the photoelectric effect were the electrons were emitted immediately. There's no time delay. As soon as you shine the light on, electrons are given off. Increasing the intensity of the light increases the number of photoelectrons, but not their maximum energy. So the brighter the light, the more electrons given off, but it doesn't give them a greater kinetic energy. And that was going against the classic theory at the time. Red light will not cause the ejection of electrons, no matter what the intensity, in this case for sodium. A weak violet light, so violet light is a higher frequency and a shorter wavelength than red light, will eject only a few electrons, but their maximum kinetic energies will be greater than those of the intense light of longer wavelengths. Okay. Now taking all this in will take a couple of goes, so don't worry if you're a little bit confused at the moment. Now the classic experiment for the photoelectric effect is this, where you have your metal surface and it's polished and it's in a vacuum. You shine a light on it and you can vary the wavelength of the light, and the photoelectrons come off the surface and go to a collector over here, and you measure the current with a galvanometer, and you can vary the voltage, and so you can have an electric field in here, and you can reverse the electric field. If this is a positive plate, the electrons are attracted to it. If that's a negative plate, the electrons will get repelled or slowed down before they hit it. Some of the key features: electrons are ejected from the metal only if the frequency of the incident light, the light that we're shining, exceeds a minimum value, and this minimum value for the metal is called the threshold frequency, and it's given the symbol F with a 0. So that's the threshold frequency. If you shine light with a lower frequency than that, it doesn't produce the photoelectric effect. Each metal has a unique threshold frequency. If light is below the threshold frequency, no photoelectrons are ejected, irrespective of the intensity. So it could be the brightest light possible, but you still won't get any photoelectrons. Once a photocurrent, so once electrons are ejected, occurs, increasing the intensity of the light increases the number of photoelectrons. Okay, so if you're over the threshold frequency, you can increase the intensity of the light and you'll get more photoelectrons. If you're below the threshold frequency, doesn't matter what the intensity of the light is. If light with a frequency higher than the threshold frequency is shown in the middle, the photoelectrons have increased kinetic energy. So there's a maximum of kinetic energy here, and as we increase the energy of the light, we increase the kinetic energy. Now there's a little animation I'm going to show you. So that should be this one. Yes, here we go. So here's our light, here's our metal, in this case it's sodium, and we're going to shine light on it. So this represents the photons. Now clearly we're not getting any photoelectrons, so we're below the threshold frequency. So if we increase the wavelength, decrease the wavelength, increase the frequency of the light, we will eventually come to the threshold. There we are, the threshold frequency, and you can see the electrons are coming out, and they're coming out with varying kinetic energies. Like some are fast and some are just dawdling along. Now if we increase the intensity of the light, we should get more photoelectrons. Here we are. Okay, so now if we decrease the light below the threshold frequency, it stops again, and if we increase the intensity to 100%, still can't get any photoelectrons coming out. Now if we go past the threshold frequency, the electrons come out with a lot more energy, and you can see some are still slow, but some are moving a lot faster, so they have more kinetic energy. And we can keep increasing the energy of the photon, so by decreasing the wavelength or increasing the frequency. And even if we get ultraviolet light, we're still getting photoelectrons. And there's some moving slowly and there's some moving fast. And that's the photoelectric effect. We'll get a little bit trickier in a second, or in the next one from that. Right, let's go back to this. Let's pause that. Anything else? If we had a different metal, yes. So if we picked a different metal, copper, and we would see, we'd work out where the threshold frequency for that metal is. It's a little bit further, isn't it? Haven't got any. Ooh. So copper, the threshold frequency for copper is, wow, way up there. Okay, so every metal has its unique threshold frequency. And we could do, let's do one more, platinum. Are we getting any? No, so we have to go up here, and there they are. It's in the ultraviolets as well. Right, let's move on. So to measure the kinetic energy of the injected electrons, we can have a varying negative potential is applied to the collector plate. This corresponding electric field, so we generate an electric field between the two plates, and if we point the electric field in the right direction, it can retard or slow down or stop all electrons from reaching the collecting plate. And this electric field is sometimes referred to as the cutoff voltage or the stopping voltage. So we're putting a voltage across the plates, we're generating an electric field that applies a force to stop or slow down the electrons, and when we stop all the electrons reaching the plate, that's the stopping voltage, and I'll demonstrate that shortly. Okay, actually let's go to it now. So let's go back to our friend sodium. So we're generating photoelectrons, aren't we? Yes. Now if we applied a voltage, this allows us to put two voltages. In this case the voltage is positive, so all the electrons ejected from this plate come across here, and we use this setup just to check if the photoelectric effect is happening. Now if we change the polarity of our voltage, we can make this positive and this negative, so the electric field is going this way, so electrons are actually experiencing a force that way. And here you can see that we've stopped all the electrons from reaching this plate. There's no current. Now if we reduce this, I don't know how accurate this is, we reduce this a little bit to about 0.2. okay, you can see that are any of them going to reach? No. So that's very close to the stopping voltage. They get this far. Not quite accurate enough to... oh, no, it doesn't let me go any further. Alright, but we could tweak that so that they just reach there, and that would be the stopping voltage. Like, as soon as you get zero current, that would be the electric field to stop it. And that's what we mean by the stopping voltage. If we moved to, what did we do? Copper, and we eject them. Okay, we're getting lots of them, so we need to increase, and we're still getting a current. Okay, and what we do is we'll just stop the current, and it will be around, ooh, see how close they're getting? So here we're still getting a current at minus 2.6 volts. We'll take it to minus 2.8. There we go. And they're still getting there. And we could reduce the energy. Alright. But if we go back to the threshold frequency, we get there. Alright, enough of that. But you get the idea. I could do that forever. Now, Einstein explained the photoelectric effect in 1905 using quantum theory. And this is the title of the paper. On the heuristic viewpoint concerning the production and transformation of light. Pretty interesting title. And what Einstein's work predicted was that the energy of the ejected electron increases linearly with the frequency of light. Surprisingly, this hadn't been tested, and so he was actually hypothesizing. And in 1905, it was known that the photoelectron's energy increased with the increased frequency and independent of intensity, but it wasn't known if it was linear. And the prediction from Einstein in 1905 wasn't actually tested for another 10 years, until it was done by Millikan, who showed that Einstein was correct. And Einstein got a Nobel Prize in 1921 for that paper, and a couple of others he wrote as well. Now the explanation: photons interact with the surface electrons on the metal. Go back to your physical science understanding. There's electrons whizzing around in metals, and so the photons are interacting with those electrons. A single photon causes the ejection of a single electron. A photon can give either all or none of its energy to the electron, so it's an all in or not. So it's one photon, one electron, or not at all. Each electron can only absorb one photon. Einstein defined three forms of energy in the system. It's the energy of the photon, that's the incoming energy given by Planck's equation, E equals hf. The work function of the metal, this is a variation of this, W equals HFO, whether that's the threshold frequency, so that's the energy required, or the work function, and that's the energy to get the electron free from the metal, and the maximum kinetic energy of the photons, or EK max. So in other words, each photon delivers a quantum of energy, hf, which is absorbed by an electron. Energy is needed to free the electron from the surface, that's the work function, HFO. If hf, the energy of the photon, is more than this, the remainder is available to the electron as kinetic energy. So the leftover energy goes to become kinetic energy, although most electrons lose some kinetic energy before emission because they interact with other atoms. And this is it. Here's the incoming photons. They hit an electron, electron absorbs it, gets ejected, has to overcome the work function. Here they use a different symbol, and what's left over gives you the kinetic energy. So there will be a maximum for the kinetic energy relating to the energy of the photon minus the work function. Some equations that we have: half mass of the electron, Vmax squared, so that's the kinetic energy, equals the energy of the photon minus the work function. Rewritten here using W and EK max and putting in the numbers. And we've also introduced here Q, which is the charge of an electron, multiplied by the stopping voltage, is equal to the kinetic energy. And on your formula sheet that you have, you're only given this. Now notice a couple of things. W is the work function, HFO, so you've got to remember that. And this EV is not electron volts, it should actually be QeV. I don't know why they write it like this, but they still do. So that's the charge of an electron multiplied by the voltage, which is the stopping voltage. So here we have a couple of scenarios. This is our metal, so we're shining a light on, and we're producing 4 different photoelectrons. So they're all absorbing a photon. This is a representation of the energy of the photon, and this is a representation of the work function. So the energy of the photon is actually more than the work function. So this electron here is close to the surface. The work function is to free it from the binding of the energy, and so it has excess energy, which gives it a kinetic energy, and that will be the maximum kinetic energy. This electron also has the work function, so it escapes, but it has to do some work to get out of the extra work interacting with the other atoms, and so when it escapes with a bare minimum of energy. It has just enough energy to escape, but the kinetic energy is 0. C is between the two, so it escapes, has a little bundle of energy, but it's not the maximum amount of kinetic energy. Alright, and D doesn't have enough, absorbs the photon, but doesn't have enough energy to escape, and therefore doesn't emit a photoelectron. Again, another explanation. I told you it was complicated. Here we have different wavelengths. So this is red light, which is at 700 nanometers. Each photon contains 1.77 electron volts of energy. Here the work function is said to be 2 electron volts. Sometimes the work function's in joules, sometimes it can be given in electron volts, just to confuse you. So this photon doesn't have enough energy to overcome the work function. It's below the threshold frequency. Green light is above the threshold frequency, and therefore a photoelectron is given off, and that will be the maximum recorded velocity. Blue light has even more energy, and so overcomes the work function and can come off with even more kinetic energy. These are some of the graphs you might see. Here we have the frequency of the light. Here we have the kinetic energy maximum. These are 2 metals, and we will see that this would represent threshold frequency. So below this frequency, no photoelectrons are given off, and they just get off here. And as we increase the light's energy, the photon energy, we get more kinetic energy max given off. This metal has a different threshold frequency, but on this graph the slope is actually Planck's constant, so the 2 lines will be parallel, because if we rearrange the formula we were using before, we can rearrange it so that the kinetic energy is equal to H bracket F minus FO, and so the slope is H. Just another graph as well. This one's been extended into the negative. Now the reason for that, This is the threshold frequency, of course, for sodium, magnesium, copper, but this would represent the work function. Now we can calculate the work function from the threshold frequency or by reading it as the y-intercept. Now, okay, the fact that photons in the photoelectric effect can give all or none of their energy is the particle-like property in the photoelectric effect. Waves can impart some or all of their energy. Particles can only give all or none. Now we're going to continue the photoelectric effect. You thought that was a lot? There's still more to come. So, see you later.